Okay guys, so today we're going to be talking about static friction. This time we're applying it to an incline. So this example is going to be static friction on an incline. So we have a 7 kilogram box is held at rest on a 25-degree incline plane by an applied force, F sub A. The box just begins to slide, but does not fully move. So we can still consider this static friction. If the coefficient of static friction between the box and the surface is 0.3, find the applied force. So you can see from the diagram here, we have the box on the incline. The incline is 25 degrees. We have an applied force pushing it up the incline. Okay? So we're going to take a look at this as if we were looking at a regular force problem. We're going to draw the forces acting on the object while it's on the incline, take a snapshot, realign the surface of the incline to be strictly horizontal, and then go to our free body diagram. So acting straight down on our object here is going to be the force of gravity, F sub G. Perpendicular to the surface, meaning two 90-degree angles with the surface, we have the normal force. We have the force of friction, which is opposite the applied force. So it might be hard for you to tell here, but the applied force is working up the incline, which means that it technically is pointing to the right. So I'm going to erase this F applied, redraw it, so it's a little bit less misleading. So force applied is going to be up the incline to the right. Opposing that force applied is mu the force of friction to the left. Right, we want to take a snapshot, and we're going to realign the horizontal axis with straight X, okay? So let's redraw that over here. Here's our surface of the incline. On the incline is our box, our normal force, our applied force, our force of friction. All three of those forces are going to straighten out. Our force of gravity is going to swing right down and to the left. So now, take a second, pause the video, draw your free body diagram. Draw it yourself. Don't wait for me to draw it and copy it down. Try to draw it yourself and then copy mine down. Okay, so for our free body diagram, for our block, we have normal force up, friction to the left, applied force to the right. Force of gravity is going to be down and to the left. That angle is the angle of the incline, which we know is 25 degrees. Now we need to take our forces and break them into components. So you know that in the y, normal force is going to be positive. 0 on the x. Our force of friction is going to be negative, 0 on the y. Messed up that third. Force is going to be force applied, it's going to be positive in the x, 0 in the y. Our force of gravity, right, it has two components, an x and y component. When we're on an incline, remember x is cosine unless on an incline. So for the x, we're going to use sine of the angle of the incline. So we're going to have FG sine theta. For x, FG cosine theta for y. Is it positive or negative? Both negative because we're down and to the left. So now we're going to sum the forces in the x and in the y. So the object is sitting on an incline. So we know that it's not accelerating. The sum of the forces in the x and the y are going to be equal to 0. So let's start with the y. Sum of forces in the y equals 0. So we're going to have F sub n minus the force of gravity, cosine theta, is equal to 0. F of n is going to equal, move it to the other side, right? We're going to take Fg cosine theta, move it to the other side of the equal sign. Force of gravity, right, is equal to the mass times gravity. So let's plug that in. So normal force is going to be mg cosine of theta. We can plug in what we know to solve for F of n. So do that right now. Pause the video. Press play when you have a value. When you do those calculations, you're going to get 62.17 newtons is our normal force. We're not done yet. We need to find the applied force. So we're going to have to sum the forces in the x. So we're going to have negative force of friction plus the applied force minus force of gravity times the sine of theta. So I'm going to erase that flow chart to give it some more room. And you guys are going to sum the forces in the x right now. So the sum of the forces in the x, negative force of friction. Most people forget to include that sign. Don't forget to include that negative sign. It's a big mistake. Alright, so we have our sum of force in the x set up. Let's plug in what we know. We know that the force of static friction is equal to mu sub s times F of n. So let's plug in for that. Plus our applied force, which we don't know, we're solving for. So we're going to leave it as a variable. Minus mg sine theta. All equal to 0. We know that mu, the value of static friction, is 0.3. Times our normal force, which we calculated right over here, 62.17 newtons. Plus our applied force minus mass of our block, which we know is 7 kilograms, times 9.8 times the sine of 25. All equal to 0. So you plug those values into your calculator, you're going to get negative 18.651 newtons plus applied force minus 28.99 newtons. So what I want to do is simplify it. We're going to add 28.99 to the other side and add 18.65 to the other side as well to solve for F of A. So for F of A, we're going to get 47.6 newtons. That's the applied force needed to keep our block on the incline without moving. Alright, so you guys can try problems 8 and 9 on your force worksheet. You should also be able to do the rest of those problems as well.